Hello students, here we are on our very last lecture, our last module. Okay, so we're looking at module 16. We're going to do the total module today, all of it. So this lecture might be just a little bit longer, but that's okay. We have just a short lab for this one, right? And so I'll discuss with you, as we go along, what we would be doing together today. All right, so we're learning about astrophysics. So, yeah, rocket science. So you can tell somebody, yes, this is rocket science. And so we are going to get into this in just a minute. I do want to talk to you a little bit about expectations. So this is our last week of classes. And so you're going to watch this video and fill in your book for that. And then you will have your final next week. So the final, I have decided, is 20 questions online through Google Classroom. Now the big question is, are we all going to be able to access that? Are all of you going to be able to access that quiz? And I hope the answer is yes, because here's the way it should work. And I'm not sure why I haven't quite figured this out yet. But you'll go online to the Google Classroom. So I'll invite you. I'll send you some sort of invitation. You'll go online and you will literally just answer the questions online. All right? And it'll grade it for you. And I'm not sure if it tells you the grade right away or if it just sends it to me. So I'm not exactly sure how that works. But it'll be 20 questions, multiple choice with one bonus question, which is a short answer. All right, so each question's worth 5 points. Therefore, you could, if you got everything right plus the bonus, you would have 105 on the test. Okay, so that's the plan right now. It is definitely shorter than the original one would have been, and that's just because we're in this weird thing, okay? But I feel like if I can get that to work properly, then we will be okay. All right? So let's get started on Module 16. Okay, so we're learning about astrophysics, and that's going to start with our sun. Okay, so our sun is our main source of light. It's a very special star. So we're going to be learning about stars today, all right? Stars and traveling out into space and that kind of thing. So you have at the top of your Lab 32, your page in your lab book, you have a little table, and you're going to write down some interesting facts about the sun. All right, so here are some of those interesting facts, and then we'll kind of cover these, one at a time, if you will. So, but if you want to write these things, what do we have? 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, so yeah. You just figure out what you want to put in there, okay? And you can pause this right now if you like. So let's talk about the sun and what it is composed of, we think, and how we've labeled it, okay? So we think there's a core that is very, very dense and very, very hot. We don't know what it is. We have some guesses. And then since it is under so much pressure and it has a lot of energy associated with it, it's burning, right? And so we have the zone around it called the radiative zone, and that's radiating that heat. And then as you see, as we move up this way, we have something known as the convective. So we have some swirling so it's hottest here. As it moves up here, it quote unquote cools down a little bit and then goes back down like this and cools and heats and cools because the heat keeps rising right there. This is what we think is happening. The outer part right here is called the photosphere, the part we're seeing, and then the chromosphere is the sort of like the atmosphere, if you will, and then the corona, which literally just means crown. It's called that because when we have a solar eclipse, the moon passes between the earth and the sun for a brief time, and when the moon is completely over the sun, it completely covers it, but you can still see the corona, and it looks like a crown. All right, and that's what the word corona means. It means crown. Right now it's a little bit of a dirty word, right? Corona, yikes, ooh, we hate that. But it was named that at the sun long before this silly virus. All right, let's get a little introduction here. Our favorite guy.
We normally think of the sun as emitting visible light, but it emits light of all wavelengths. This animation, for example, gives you two views of the sun as it spins on its axis. On the left, we're looking at the X-rays that are being emitted by the sun, and on the right, we're looking at the visible light that's being emitted by the sun. Now, X-rays cannot be seen, of course, so what you're looking at on the left is really just a representation of the intensity of X-rays coming from the sun. Notice that as the sun spins, there are dark spots on the right-hand side. Those are sunspots, areas in which the sun is emitting less visible light than normal. Notice on the left-hand side that those same areas of lower visible light emission correspond to high levels of X-ray emission.
Very cool. All right, remember, it's kind of hard to study the sun because it's so bright. So when we train any telescope on it, it has to have these incredible filters on it, which of course reminds me to remind you to never ever look at the sun, right? Bad for you. All right, so what zone is the hottest on the sun? I believe this is a question you have. What zone is the hottest on the sun? We believe it's the core, and we believe it's about 27 million degrees Fahrenheit. You know, how do we know that? Well, it's mostly math, okay, math calculations. We have an idea of the surface and what the temperature is there, so therefore we can extrapolate that information and make a pretty good guess. Once again, it's a guess, like all science, right? Okay, so you're going to write that down, 27 million degrees Fahrenheit. This is meaningless right now. Okay, we'll get back to that. All right, so our star is the sun. So what is the coolest zone on the sun? He mentioned that in the video. Did you hear that? All right, the coolest zone would be at the photosphere. Okay, so that is the surface of it, and it's 10 million degrees Fahrenheit. All right. We are getting now. The reason we have made so many guesses about the sun and what's going on in the sun is because we're able to, by looking at it, to look at the gases through a spectroscope. So you may recall that I had those little spectroscopes that we used on video because we weren't together, where I looked at it, the light through it, and you saw the little rainbow on the side there. Okay, so that's a spectroscope. It's a very simple one that we use in class. The fancier ones, you can train a spectroscope on any star or anything for that matter, and if there's gases in it, they will emit a certain color. All right, so particular elements release particular colors when you burn them. I do this with my chemistry class. We literally take chemicals and we burn them, and you see this incredible color coming off of them, and because of that color, you can guess what element it is. All right, so when we train the spectroscope on the sun, we see two main element colors coming off of that: hydrogen and helium. All right, so which has led us to believe we know what's happening on the sun as far as the fuel goes. All right, so the gases on the sun are hydrogen and helium, and then 1% other gases. You know from your study of the periodic table that hydrogen and helium are the two lightest elements, right? They're elements number 1 and number 2. All right, so we know that hydrogen has 1 proton, helium has 2 protons. There it is, 74% hydrogen, 25% helium. Excellent. Let's look at some flares. We're going to get back to those gases here, y'all. It's pretty cool stuff. All right, we have something, a phenomenon on the sun, which is pretty cool. They're called solar flares. With this, think about a fire. If you're watching a fire, every now and then you'll see a big flame jump up, right? Okay, it's sort of like that. So we have this combustion going on, and at the top of it, so at the photosphere, we will sometimes have these large flares that pop up. And that's what's creating that chromosphere, and then ultimately the corona. And some of them are smaller, although they're quite big, and some of them are huge. So those are called prominences, the ones that are very, very large. Here's a picture of one. That might be a prominence, but I think it's a flare. Look at the Earth to scale there. So you see how large that is. All right, so it turns out when there's a lot of solar flare activity on the sun, it actually affects us down here on the Earth. And one of the main ways that we experience that effect is that it interferes with our cell phone reception. All right, so there may be times you're like, wow, my cell phone's not working very well. We may have just really big solar flares. The other thing that the solar flares, increased solar flare activity will do is cause an increased activity on the Earth of the northern and southern lights, so our auroras at the poles, which are also related to the magnetic field as well. But those solar flares do influence it for sure. All right, this is a little, a little GIF of this. You can see that splurting out, and I want you to notice, does it show us the whole way down? Because it's going to fall back into the sun. Okay, it's not gonna come off the sun. So I don't want you to think that those solar flares are actually coming off the sun. Notice that's getting sucked back in. What's sucking it back in? You should know the answer to that. That, of course, is gravity, right? Gravity is sucking it back in. I think we're back on a loop here. So what happens, though, is it sends out what we call a solar wind. So there is something coming off of there. We don't really see it, but it comes off of there, and that's what ends up hitting the Earth. So, and then furthermore, the Earth has a magnetic field. We know this, and when the solar wind comes toward it, the magnetic field serves to deflect it away from us, so it protects us. So really, our magnetic field is protecting us from the solar winds being too strong. But they do come in at those poles and cause that aurora to take place. This is a video showing you some prominence. So let's watch it a little bit. This is NASA-made video. Now, there's going to be some sound associated with this, y'all, but I need you to remember that there's no sound in space. So the sound is the machine, okay, the machine. So let's watch the activity. You get the idea here. All right, which leads us to something else. So we have what we understand to be the states of matter, right? The states of matter. These would be solid, liquids, and gas. But there's a fourth state of matter known as plasma. And in the old days, I used to always say, well, plasma is the stuff of stars, right? It's the stuff of stars. Well, it turns out we have plasma all around us. And so right here you can see something on this ship. These little like electrical signals. This is called St. Elmo's fire. And a lot of times sailors would recognize it, they would see it, and they would wonder what it was. They, of course, attached some sort of superstitious events to it, thought that God was trying to reach them, things like this. But it turns out it's just plasma. And you can see here that the plasma is what's going on inside the sun. Now, we need to understand a little more of what plasma is, just because it's interesting. I don't know that your book talks about it. But we are looking at solids, which are arrayed like this. You know, they are closely attached together. We know that our liquids, of course, are very fluid, right? So taking solid, adding energy in the form of temperature, we'll turn it into a liquid. So this will break up into fluid, and those molecules will be moving past one another. We add energy and temperature, and we'll turn it into a gas. And then we have the molecules very far away. Well, now if we get it hotter, if we can get it hotter, we can see what happens. Some things weird go on here. Okay, we got fragments going on here. We've excited gas molecules and this crazy stuff. And so, you know, that takes a lot of energy and temperature that way, but we've been able to sort of tap into that. Let's watch a video about it.
Have you ever seen static electricity cause a spark of light? What is that spark? What about lightning, the northern lights, or the tail of a comet? All of those things and many others, in fact 99.9% of the universe, are made of plasma. Plasma is a state of matter, drastically different from the more familiar forms. Take ice, for example. Ice, a solid, melts to become water, a liquid, which, when heated, vaporizes into steam, a gas. Continued heating of the steam at a high enough temperature causes the water molecules in it to separate into freely roaming hydrogen and oxygen atoms. With a little more heat, the ionization process occurs, and the negatively charged electrons escape the atoms, leaving behind positively charged ions. This mixture of freely roaming negative and positive charges is plasma, and at a high enough temperature, any gas can be made into one. These freely moving charged particles behave very differently from the particles in other types of matter. When a doorknob, a solid, has static electricity on it, it doesn't look or behave any differently. And with the exception of a compass or other magnetic object, we rarely see matter respond to a magnetic field. But put a plasma in an electric field or magnetic field, and you'll get a very different reaction. Because plasmas are charged, electric fields accelerate them, and magnetic fields steer them in circular orbits. And when the particles within a plasma collide, or are accelerated by electricity or magnetism, light is generated, which is what we see when we look at plasmas like the aurora borealis. Plasmas aren't just beautiful celestial phenomena, though. Imagine a tiny cube, made of normal gas with a very high voltage across it. The resulting electric field pushes some of the electrons off the atoms and accelerates them to high speeds, causing the ionization of other atoms. Embedded impurities in the tiny cube of gas cause it to gain and release a precise amount of energy in the form of ultraviolet radiation. Attached to each tiny cube, a fluorescent material glows with a specific color when ultraviolet light at just the right intensity reaches it. Now, make a rectangle out of 1,000,000 of these tiny cubes, each separately controlled by sophisticated electronics. You may be looking at one now. This is called a plasma TV. Plasmas also have implications for healthcare. Plasma chemists create highly specific plasmas that can destroy or alter targeted chemicals, thereby killing pathogenic organisms on food or hospital surfaces. Plasmas are all around us, in forms that are both spectacular and practical. And in the future, plasma could be used to permanently rid landfills of their waste, efficiently remove toxins from our air and water, and provide us with a potentially unlimited supply of renewable, clean energy.
Wow, cool stuff, y'all. That looks like something that we could use now, right? If it's going to kill microorganisms and weird things like viruses. So getting into this as a field or as a career might be a real lucrative thing to get into. So we're just basically just touching the tip of this whole plasma thing, yet it's all around us. How about that? It's not just the stuff of stars, right? It's all around us. Okay, so now let's talk about what we think is happening on the sun. Okay, so what we think is going on is that there is something known as nuclear fusion. Okay, remember to fuse some things together. So right here at the top, I say nuclear fusion powers our sun. It should probably say nuclear fusion probably powers our sun. All right, we have pretty good data, and that data has to do with looking at those gases, seeing we have our hydrogen, seeing we have our helium, and seeing lots and lots of energy being produced. So therefore, the idea that a hydrogen is fusing with another hydrogen, that's one proton fusing with another one proton, and what do I end up with? An atom with two protons, and what is that? Helium. All right, so that's what we think is going on. And because in order to do that, it takes an immense amount of power, it actually, when it finishes, releases a lot of power. Okay, we think it's probably the most powerful thing we know of. And we're really, really trying hard to see if we can reproduce this on the Earth. So far, we have not. I mean, on a very limited way in a laboratory using massive expense to do it. But if we can do this affordably, then we can power, we got lots of hydrogen, right? That's a seriously, renewable resource. We can, it's hydrogen, we can't make it, but it's around all over the place. We can generate it out of water, we can generate it out of air, we can generate it, free it up, if you will. All right, so the fusion of two hydrogen nuclei to make helium with a huge release of energy, which brings us to this famous energy equation. So remember, we've talked about this. We've talked about the fact that energy and mass and the speed of light. Remember, we put time in there. We looked at Albert Einstein's ideas here and how time. Remember that weird video about when we're going, if we're going the speed of light, then time gets to be minimalized because the energy and the mass and the time are all related to each other. That's our famous energy equation, our famous relativity. Everything's relative, right? So there it is. Energy equals mass times the speed of light squared. And we know that the speed of light is constant, or at least we assume that it's constant at this point. Okay, so when it comes to fusion, let's see how that might be happening.
In nuclear fusion, two smaller nuclei join to become one larger nucleus. For example, here I have two isotopes of hydrogen. Hydrogen 1, which just has a proton, and hydrogen 2, which has a proton and a neutron. If they collide just right, they can join together to form a nucleus that has two protons and one neutron. That's helium-3. The other thing produced here is a lot of energy, and this is one of the fusion reactions that provides energy for the sun.
All right, so that's what seems like is going on. Let's check something else out.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
All right. Remember, that's our best guess. So we have something we know about that we do here on Earth right now called nuclear fission. We've actually studied it. So which one's better as far as generating energy? Well, fission is the process by which a large nucleus is split into smaller nuclei. Remember? Radioactivity. So we've already looked at that. And so we know how that happens. We have beta decay and alpha decay and that kind of thing. But nuclear fusion would be the best energy source. There's no radioactive waste that's produced, right? We've got our hydrogens. That's a pretty easy element to locate rather than digging and mining for uranium and plutonium and those big ones, right? So if we could figure out how to do fusion, it would be better for sure. All right. So have we seen this already?
In nuclear fission, a neutron bashes into a large nucleus, such as uranium-235, and splits it into two smaller nuclei, like this. Notice that the fission not only produces two smaller nuclei, it also produces a few neutrons. Those neutrons can go start fission reactions with other uranium nuclei, producing even more fissions, which produces even more neutrons. If this is allowed to continue, eventually you have a chain reaction and a nuclear explosion.
Okay, so you see how we had the decay. So we've seen something similar to this where we see that radioactive decay is creating these new daughter particles, right? So we're going to see an application of that today. All right, so that brings us to the idea of how can we use this to make a bomb? So we do that by reaching something known as critical mass, which then creates a chain reaction. So I think you're going to write this down. A chain reaction is a reaction that will continue to split atoms as one completes and another reaction starts. So the first one comes in, our neutron. We have new neutrons splitting out and hitting more. And if that keeps going exponentially there, then we can have this chain reaction reaching that critical mass. So what is critical mass? The amount of isotope necessary to sustain that chain reaction to produce the nuclear fission on a grand scale. Okay? So we have our fissile material. This is not enough to make that chain reaction, so therefore it's considered subcritical. Then we get to critical mass. That's just increasing the mass, so we have more of that radioactive material. And then we will see what happens when we let that chain reaction proceed. We'll get to something like this, a nuclear explosion. Now, there have been used in warfare 2 nuclear bombs used in the history of our world. That was in 1945 when the U.S. dropped 2 nuclear bombs on Japan to bring about the end of World War II. Now, since that time, there have been many other ones that have been tested by various countries. All right, so we're not the only ones that have a nuclear bomb. First, it was just America. Then spies took all the information to Russia, actually the USSR. So we had the Cold War and all that kind of stuff. And now we have several countries that do possess the technology and actually have a bomb. So in order to protect themselves mostly. Nobody's used it. Now this information is review as far as I know. We know that nuclear fission creates cheap, effective energy, but it also presents dangers. So we know about a nuclear power plant, right? We already talked about this. The meltdown can be the uncontrolled heat that causes the fuel rods to dig down through the reactor vessel. Remember, that's called the China syndrome. If they get through the containment vessel, which in America that hasn't happened, but it did happen in Russia at that Chernobyl situation, we could have radioactivity that contaminates the air. All right, so this is just a review. Here are our fuel rods that are always being bathed in water, keeping them cool, but the heat, of course, is causing steam, water to boil, and turbines move, and I got energy. If some reason the water vacates the core, then those can burn down through there. And we know that that is a problem. Typically that happens with just, human error or computer error. These are the areas where we have nuclear power in the United States. The U.S. is the #1 producer of nuclear power. Is nuclear power safe? I think we've discussed this. We've decided yes, it is, as long as we treat the radioactive, waste properly, which I don't know. That's a tough one. All right, let's watch a video.
What is nuclear energy and how does it work? Since the beginning of the Industrial Revolution, the demand for energy has increased dramatically year after year. Today, the majority of this demand is met with the combustion of fossil fuels. With the recent disaster at Fukushima, as well as the ever-present effects of the events at Chernobyl and 3 Mile Island, nuclear power has lost some of the enthusiasm that once surrounded it. Because of the rising costs and harmful effects on the environment caused by fossil fuels, people are looking for ways to replace our dependence upon them. While renewables such as hydroelectric, solar, and wind energy have proven to be worthy replacements, they are still a ways off from meeting our needs. Nuclear, on the other hand, has all of the technology required to be used on a large scale. In the US, nuclear accounts for 21% of the electricity produced, whereas coal contributes 41%, natural gas 24%, renewables 12%, and petroleum only 1%. Despite the current level of adoption, there is still a great deal of misconception and fear surrounding nuclear energy. Now, let's see how most nuclear power plants actually work. First, you have the fuel, usually uranium, which must be mined, enriched, and then formed into pellets that are placed in rods within the reactor. The atoms of uranium undergo a controlled chain reaction which emits heat. Pressurized water around the reactor vessel is heated and circulated through pipes in a steam generator, which produces water vapor that spins a turbine attached to a generator. After leaving the turbine, the steam is condensed so that the cycle can continue. The benefits of using nuclear fuels are numerous. The lack of carbon emissions, the ability to create huge amounts of energy, and the reliability of power production are all extremely important. As there are no fossil fuels used in the consumption of uranium, direct carbon emissions are non-existent and indirect emissions are limited to the construction of the facility and obtainment of fuel. Unlike many renewable methods, nuclear plants do not depend on the conditions around them to function, which would make them perfect for the constant baseload of the electrical system. The main concerns surrounding nuclear energy are safety, waste management, and total expense. Contrary to popular belief, nuclear is among the safest sources of energy that is currently in use. Despite the seemingly huge impact reported by the media, there have been no deaths as a direct result of the meltdowns at either Fukushima or 3 Mile Island. Even in the case of Chernobyl, the total number of expected deaths is quite low. In comparison, deaths due to the use of coal are over 10,000 per year in the US alone. However, deaths are not the only impact which an accident can have. They can force people out of their homes and change the land around them for a very long time. For the treatment of waste, there are 2 main options that are currently employed: containment and reprocessing. Containment is the placement of exhaust fuel in safe containers where it will remain for a very long time. The second, and more expensive method, reprocessing, treats the waste so that it can be used within a reactor again. Nonetheless, reprocessing is not currently practiced in the US due to a lack of facilities necessary. Furthermore, costs come mainly from the building and regulation of plants. These high initial costs can be mitigated by focusing on uprating current plants instead of building many new ones. Finally, technologies are being developed which can further decrease these disadvantages. So then, how can nuclear play into our energy future? Combined with renewable sources, nuclear allows us to enjoy our energy needs without the impact on our environment that is coupled with fossil fuels.
All right, there we go. Okay, so that told us. I will say that those containment vessels, for putting the waste in there, that sometimes they can leak and stuff like that. So that's what people are concerned about. All right, so this would be the end of our class if we were together for 16A. We're going to go on to 16B, of course, right now. But the idea here is I've got a hydrogen, and they fuse together, and they make our helium. Now, we can't do nuclear fusion in our lab because we can't do it at all, right? Because it takes an immense amount of energy to do that. But I would love to inspire you to think of a way that it could be done affordably. You could be a quadrillionaire. That's right. All right, so but we do talk about going to the stars as far as rocket travel, so we'll get to that at the end of the thing. This is today you're going to use your little rocket deal. So this brings us to 16B, so go ahead and turn over to Lab 33. We're going to look at star types, so not just our star, but other stars out there, and then how they're formed into groups, galaxies, and so on. All right, so let's move on to that. All right, we classify stars based on a couple of things. Temperature and magnitude. So that's probably, I've got those underlined, which makes me think you're probably going to write those down, right? Yeah, so by temperature and magnitude. So you can see that the cooler ones are on the red end over here, 3,500 K. And they move up. Blue is the hottest star out there. So what does it say? Just like car headlights look small and dim when they're far away, and they blind you as they get closer, stars are similar. So if the closer they are, the brighter they look, that kind of thing. But the color has to do with their temperature and how they're burning, and sometimes size as well. You might be surprised to find out some of the hottest ones are actually smaller in size, and some of the cool ones are actually quite large stars as far as their size. All right, so we have these things called spectral letters. They're assigned by the temperature. So here we go. Here's our spectral letters, okay? Right over here. And this is representing the temperature. And then this, our conventional color, apparent color. So there are shades of blue. Then we have white to yellowish white. Yellow. That's yellowish white's over there too. Orange, red, and orange red, that kind of thing. Okay. And remember that has to do with the temperature. And then we have this class or spectral class we put them into. So some examples we can look at. For our sun, our sun is a yellow to orange right here, and its surface temperature falls into this range. A very hot one is called Rigel. Rigel is in the constellation Orion. Sirius is white. It's in the constellation Canis Major. we have Aldebaran in Taurus and Betelgeuse and also in Orion, okay, which is a cool star. When I say cool, you know, it's a 3,600 to 2,000 degrees. It says C right there, so Celsius. So what is the magnitude? The magnitude is how bright something looks to us, okay? So the brightness of it. But the brightness is for us is based on where we are on the planet Earth, okay? So that's called the apparent magnitude. All right, so let's look at the absolute magnitude. That's the brightness of a star that's been corrected for how far away it is, okay? So in other words, we tried to figure out how bright a star is if we were as close to it as our sun is, okay? So it's on a scale of -8 to +19. The smaller the number, the brighter the star. You're probably writing that down, okay? The smaller the number, the brighter the star. Then we have the apparent magnitude, and that's how it's seen to us. We look up in the sky at night, we see an array of stars, we say, oh, that one's brighter than that one, okay? And then we have a smaller number, once again, the smaller the number, the brighter the star. So the absolute and the apparent are similar in that way. It's because we're looking at brightness. So here we see we're on the Earth. Our apparent magnitude of our sun is 3, right? And the absolute visual magnitude is 0.8, all right? So brighter. And that has to do because it's the distance it is from us. Okay, so that's just showing you the parsec is how long it takes for the light to reach us. I think it's 4 minutes. So here's our apparent magnitude. We're looking at this is, I think it's Orion, right? Because we see Sirius right there. Or is this Canis Major? We'll see. All right, so this is the apparent magnitude, how it looks to us. This looks like the brightest here, but if we were able to be close enough to these stars, look how much brighter these guys are down here. All right, they're just really far away. Okay, they're really far away, so we don't see them as brightly. So here's a picture of the night sky. That's beautiful. Okay, this is obviously taken by a very good telescope, probably the space telescope called the Hubble. And that's because we can see this cool stuff over here, the smoky looking stuff right over here. That stuff is called nebula, and nebula is probably star dust, a star that's exploded or something like that. Okay, now looking at sizes. So this is our sun, and then we see some other stars, okay? So they get, look how, we know our sun's pretty big. It's perfect for us, right? The whole Goldilocks idea, our sun is just right, and we're put in just the perfect place for our sun to bring life, right? But we have bigger stars. There's smaller ones as well, but you know, it generally is small compared to the other ones. So then we have some bigger stars. We get up to the giant star. Now take this giant star and put it right there. We have super giant stars. Wow. Okay, so here's our sun, and here's some bigger stars. Here's Regal, and we saw Aldebaran earlier, and there's Betelgeuse, and what is that? Antares, is that what that says? I can't quite see it. Okay, so you see how our sun compares. So in order to understand these a little bit, and especially, you know, from where we use something called the HR diagram. It stands for the Hertzsprung-Russell diagrams. Two guys that were working on this to just categorize them so we could grasp them a little better. So placing stars on a graph according to their temperature and brightness. So we look at all of them, we classify them, we put them on a graph, a chart, all right? So the spectral letter is determined by the star's temperature. So using the absolute magnitude, we have to figure that through math, right? Of stars with their temperature places them on this diagram. And it's kind of interesting because the diagram ends up looking like this. Okay, so we have this interesting swoop coming down here, making this kind of pattern, if you will. It was kind of surprised them a little bit. We have some outside of it, right? So we have some hanging out over here, the supergiants and the giants, and the white dwarfs. But the vast majority of the stars out there fall into this swoop that we call the main sequence. Our sun is in there, okay? Our sun is in the main sequence. This is kind of a picture of it too. You see the swoop right here. You see some of those giants and supergiants out there. You see our little dwarfs out there, okay? And this is showing us the temperature, okay, and the size, okay? All right. So seeing our apparent magnitude, we have those numbers, right? From, did it say positive? I thought it said positive 19. That's what we see. We can't see anything anymore past here. And then what did we say, -8? But look, sun, that's the sun. It can't really be compared to anything else. Very, very bright. Okay, so we have other things in our sky. So we're not counting the sun when we're talking about looking at the apparent magnitude of stars. The sun's in a special place. But we can see Venus is a planet, which is very bright. That's that first star you see in the sky. But Vega looks like it's one of our brightest stars in apparent magnitude. Look here. We just see right in here, right? Because this says faintest that the naked eye can see. All right, so then and then we can see faintest objects with machines like telescopes and things. All right, so then we're going to look at something known as variable stars. So we look out there at the stars. We say, oh, this one is this bright. We do the math, and we find out its apparent magnitude, and then it changes. And we think, what is going on there? So it turns out there's something weird out there called a variable star, and we're going to look at some different explanations for that. This is an artist idea of some sort of, it's pulsar, sending stuff out, and it gets less bright when it shoots some stuff out. We don't know if that's what's happening. It's a guess. Another thing that could explain it would be something known as a supernova. So the supernova, the best we can tell, is when a star collapses on itself and then explodes. Essentially, it's the death of a star. Okay, so an explosion. So we call it, what is a supernova? An explosion of a star. And it leaves behind something called a nebula. I mentioned that briefly a minute ago. A nebula would be the stardust. What's left over after this thing exploded? It kind of floats there in the air. So like you think of a firework exploding in the sky, and you can see that sort of smoke kind of drifting there for a while. It's kind of like that. It's kind of like that little smoky stuff that's left behind. This is the most famous of the nebulae out there because it's the first one we figured this out for. It's called the Crab Nebula, and way back in the 500s AD, the Chinese astronomers had seen a star in the sky, and they had studied it, and they noticed that it was getting brighter, and they thought, well, that's strange, and it got really bright, and then it disappeared. So we think what they witnessed was the death of a star, that it got real big and exploded. So they kept really great records of where they had been looking in the sky. Much later, many years later, 20th century, we put our telescope in that general area, and this is what we located. We located this nebula, and we think that's the leftovers of the thing that they watched explode. That's what's given rise to that theory. All right, so let's watch a little thing.
When a supernova occurs, a star explodes violently, creating as much light as 10 billion of our suns. Now, there was a lot of matter in that star, and because of the explosion, that matter begins to expand outward. Eventually, what's left behind is a diffuse cloud of gas and dust called a nebula. The gas and dust often interact with light from other sources and often form a glow, as shown here.
There we go. Then there's another explanation for these variable things. A binary star. This is a group of stars that are twirling around together. They're sort of tied together like like they have a bar between them or something. They don't, but they're rotating around each other. Okay, so kind of like this. And every now and then, what will happen is one of the stars, they're going around each other, that they will come in front of it and have a little eclipse situation going on. So here's what happens. They're swirling around, and sometimes one star comes in front. So we're looking at the brightness here. It's this bright, and then an eclipse happens, and it's not as bright anymore. And then they get back to this level, so then we have same brightness. Then that little red one moves behind that one, secondary eclipse. It changes brightness again, but not as much as before, and then over again. So we see this little pattern going on. So this is our idea of what might be going on there, is we have this eclipse situation. So it causes bright star, not so bright star, bright star, not so bright star, that kind of thing. So that could be an explanation for some of our variable stars. So if we're going to try to figure out that magnitude, that absolute magnitude, we need to know essentially how far away the star is and how big it is, right? We can kind of guess that on color and temperature and that kind of thing. So we use something called the parallax method and the apparent magnitude method, two ways that star distance from the Earth can be calculated. Okay, the closer the star, let's see, the parallax method, here we go. The closest star to Earth is our sun. The next closest is called Proxima Centauri. Proxima, it's got close proximity to us. It's 4.3 light years away. So there's this formula they use to calculate how far away they are. We'll look at it a little bit in a second. We don't have to do it. It's a good thing. A star closer to Earth will appear to move faster than the one that's far away. Okay, that's a helpful thing. And the change in position of one star in relation to another is known as parallax. I think you might need to write some of this stuff down, so you may want to pause right there. So here we are. Here's the Earth. So what we do is we calculate, you see we got angles and stuff going on here, at a particular time in June, all right, when we're 90 degrees from the sun. All right, so that is called the summer solstice, right? And then the winter solstice, we look at a star when we're at this angle and a star when we're at this angle, and we use our parallax angle right here to then do some complicated calculations, which, like I said, we don't have to do in here, and it can give us an idea of how far away it is. Here's another way to look at it. So when I'm looking at it in January, it looks like this. When I'm looking at it in July, it looks like this. I'm not sure why they didn't say December and June. I guess just different times of the year. Okay, so I've been mentioning this a couple of times about a light year. What exactly does that mean? Well, it's the distance light could travel along a straight line in 1 year. All right, it's very fast, right? Light moves so fast that it can travel a long way in 1 year. So in a year, it'd be 6 trillion miles. 6 trillion miles, wow. The closest star to us other than the sun is Proxima Centauri, 4.3 light years away. It says here, remember that stars twinkle and planets don't. That has to do with our atmosphere and the distance they have from us. And if you look at that, when Venus comes up, the first star we see, it does look very steady in the sky. So from the Earth to the Moon, it takes 1.29 light seconds, not years. Earth, 8 light minutes, okay? Earth to Mars, 12.7 light minutes. Earth to Proxima Centauri, 4.3 light years. And Earth to the other side of the Milky Way galaxy, our galaxy, 52,000 light years, okay? So this is one argument for a very, very old universe, okay? Because if I can see something that's 52,000 light years away, wow, that's a long ways away. How can I see that if the Earth were young, right? So good argument. So I would probably argue against it, saying that when God created the universe, he created it complete. In other words, the light was here first. You can almost say the light started here and went to the star, if you will. I know that sounds weird, and philosophically it gives me a headache. But it is a good argument, right? Here we're looking at the night sky. So these big bright ones right here, those are planets. Okay, so that planet, I don't know, maybe that's the moon. It looks so big. But typically the brightest one we see in the sky is going to be Venus. So let's just say if it looks awful big, but Venus, then that might be another planet like Jupiter or something like that. And there are certain places you can go online to figure out what I can see in the night sky, right? And so like tonight, you can say these things will be visible. Every now and then, if there's something spectacular, it'll be in the news, that we can see Mars and Venus and, Jupiter, and they're lined up and this kind of thing. They look great. So let's talk about those galaxies. There are different shapes of galaxies. We have a spiral galaxy, a lenticular galaxy, an elliptical galaxy, and irregular galaxy. And the spiral galaxy can be broken down into a regular spiral and a barred spiral. So what is a galaxy? Here is the definition. A large ensemble or group of stars all interacting through the gravitational force and orbiting around a common center. All right, so there's our official definition. I think you probably want to write that down. And you have a little chart to put in the galaxy shapes right there. All right, types of galaxies, here they are. So some people think that the Milky Way is a spiral. Some people think it's a barred spiral. I think I'm in this camp, that we're more like a barred spiral. So officially, spiral, or barred spiral, I would accept those. Here's some other ones. We have the lenticular, like a lens. Elliptical, did we talk about that one? Irregular, they just have no form to them. And this, look one, peculiar. That's a peculiar galaxy. This is our Milky Way. We're, of course, in it, so we're looking at it from our perspective out. Now, it's called the Milky Way because it does look like somebody spilled a glass of milk across our sky. Because we live so close to Austin, even us out in the country, we don't see this as strongly as we could. But if you get out to a place that's really, really dark, out in West Texas in the mountains, that's why they have McDonald Observatory there, you can see a pretty spectacular display of the Milky Way. And it looks a lot like this. And remember, all that milkiness is a bunch of stars, right? They're just really, really far away. And this is what... I'm not sure if that's an actual picture. It had to have been taken by a probe. Perhaps it's an artist's rendition of it. So it looks very spiral here. And here we can see this is a scientific representation of it. It looks very barred spiral right here. So where are we? Let's see. Do y'all see us on here? The sun. Okay, so there's our sun right here. So we're in this arm of the Milky Way galaxy. That looks very barred. And then we see Orion is in here. The Orion is a constellation. These other ones are constellations right here. And they're in different arms of our galaxy. And we see them in different ways. Okay, furthermore, we take our galaxy and we put it into something called a local group, which includes the Triangulum and the Andromeda galaxy. And then we put them into a supercluster. So we're in this thing called the Virgo supercluster, all right? And we're getting this data mostly from pretty fancy telescopes.
This NASA animation kind of gives you an idea of where we are in the universe. We start at Earth and we're moving towards the sun. We just passed a satellite. There's Venus. Now we've hit Mercury. And there's the sun. Now we're going to start moving outward from the sun, so we're backing out of our solar system now. And now you're seeing a few other stars. We're encountering some gas now. You can still see stars in the background. Now we're going to start passing through a really thick cluster of stars. Turns out we've passed through one of the arms in the spiral Milky Way galaxy. Now that we've backed out, we can start to see the shape of the Milky Way galaxy. Now remember, not all galaxies are spiral, but the Milky Way is. As we move away from the Milky Way, we start seeing other galaxies that compose the cluster called the local group.
All right, good deal. Now let's look at some constellations. We can relate to these because we see them in the sky. All right, so they appear to be in patterns. They're not really in those. They just look that way to us. There are 88 official ones. They move across the sky throughout the year. We can see the Big Dipper at one point in the sky, one part of the time of the year, and a different part of the sky in a different time of the year. So this is what we see from our vantage point. Looks like a Big Dipper. It's part of the constellation known as Ursa Major, the Big Bear. But really, those stars are distributed like this, okay, way out there. So it's just a perception on our part. Do you see the Big Dipper? All right, so here's the handle. Here's the bowl. Notice it's dumping out, all right, at different times of the year. I like this one even though it's Russian or something. So at different times of the year, it's either upward or downward, all right? If y'all read Russian, maybe you can tell me what months those are, okay? But they tend to, of course, it goes around like this because it's in that part of our sky, so that we see it all the time. Think about people in Australia, they don't ever see it. They don't see the Big Dipper. And notice also, if you follow the end of the cup here, and you follow it, it always points straight to the North Star. And the North Star just kind of wobbles in the northern part right there. All right, just wobbles. This is another one called Cassiopeia or Cassiopeia. It forms a big W in the sky. I know I see that out in my, I guess, southeastern, no, that's not right, the northern sky, yeah. And then it moves, of course, during the year. Orion is one of the most popular. We see this very commonly in our sky. You've seen it. You can really tell by the belt right there. It's called Orion's belt. This is an amazing group of stars here. And then this is supposed to be hanging down his scabbard for his sword, right? And then he's standing there. Remember, this is a big star called Betelgeuse that's in his shoulder right there. So how is this representing Orion the Hunter? I don't even really know the story of Orion the Hunter, but he was rewarded for his hunting prowess by being put up into the sky as a constellation. So here's what somebody is thinking they're looking at. All right, there's Betelgeuse. I don't know if there's something he's holding up here. He's holding maybe in some places you can say he's holding a shield. Some places he's holding a bow. Some places he's holding a dead lion, okay? And you see here's his belt. And then let's see a picture here. Here he's holding a shield. So there's his belt, there's his scabbard. So this is the most identifiable part of that. There's Betelgeuse in his shoulder, sword, this kind of thing. So I don't know if you agree with that looking like a hunter. I don't know. We just know it's Orion. All right, in order to see some of these things better, we had to develop some greater technology. And this man, Edwin Hubble, had an idea, and his idea was, we are limited in what we can see in space because our atmosphere is acting like a lens, and that lens is changing those stars that we're looking at somewhat. It would really be great if we could get a telescope out of our atmosphere into space, and it would be able to see things without the limitations of our atmosphere. And so he had this idea, and later we developed something known as the Hubble Space Telescope. And he said when we look at that, we can see something called redshift. Redshift is, we know this actually, remember we talked about light and how if things are moving away, the Doppler effect, it'll actually move toward that, or what we call redshift. We'll watch a little something on it right here, which can lead to something known as the expanding universe. If it's moving away, it's going to put out this spectral color of red to show that it's actually moving away. And therefore we can explain an expanding universe. So if it started at something real dense and small and expanded, that's a Big Bang, right? So the idea of the Big Bang theory, I don't have any trouble with that. Somebody still had to bang it, right? And that would have been God. If he wanted to use that theory, he could have used that theory, right? Okay, so we talked about Doppler effect and sound especially, right? And the lower pitches, the bunched waves, the higher pitches. Well, the same thing's happening with light waves, right? So we see if they're stretching out, we're going to see the redder light. And therefore that shows that this thing's moving away from us. If it were moving toward us, we would see it compressing the light waves, and we would have a blue light. That's called blue shift. But what we're seeing is redshift. Let's watch a little thing about it.
In this podcast, I'm hoping to talk about redshift and the Doppler effect, and how this relates to models of the universe expanding and the theory that the universe began with the Big Bang 14 billion years ago. But first, the Doppler effect, or Doppler shift. This was first named after the Austrian physicist Christian Doppler, who proposed it in 1842. And what this states is that there is a change in frequency of a wave for an observer when there is movement relative to the source of the wave. And this can commonly be seen when a vehicle producing a siren or horn approaches, passes and moves away from an observer. For example, if you were standing on a street and an ambulance approached and passed you, first of all, as the ambulance approached you, the sound waves produced in front of the siren would be compressed together as the ambulance moves towards you. This compression of the sound waves gives a higher frequency or high-pitched sound. As the ambulance moves past you, you would hear the sound exactly as it's produced. As the ambulance moves away from you, the sound waves from behind the ambulance are stretched out, giving a low-frequency sound or low pitch. The same thing can be seen with light waves, and particularly light waves produced by stars. For an observer, if a star was moving towards them, the light waves produced by the star in front of the star would be compressed together, giving high-frequency light waves. High-frequency visible light is of a blue colour, so we call this blue shift. If a star is moving away from an observer, the light waves produced behind the star would be stretched out, and this would give low-frequency light waves, and low-frequency visible light is of a red colour. This can be seen with stars when we look out in the universe, that the stars have a red tinge or red shift as we call it, showing that all the stars are moving away from us. This indicates that the space between stars is getting bigger and therefore the universe is getting bigger. The further away the stars are, the bigger we see this red shift, so the universe must be continuing to expand. Physicists have theorized that if the universe is getting bigger now, then we rewind, we could take the universe back as it shrinks and shrinks to 14 billion years ago when the universe must have been very, very small. And by using this, they've come up with a theory of the Big Bang, being the beginning of the universe. I hope this podcast has helped a bit to
All right, so like I said, I have no trouble with the Big Bang Theory. I just believe that somebody had to put that matter there and somebody had to bang that matter. Okay, this is just like a picture of this supposed red shift from the Hubble Space Telescope. But let's get into telescopes. If we were meeting together today and doing 16B apart from 16A, 16A we're going to shoot off the little rockets. 16B we're going to actually make a little telescope. They're, made with like a paper tube and these little lenses and stuff like that. And we would work in groups, but they're pretty cool. If you have a telescope, that would be great if you wanted to start using it this summer to take a look at some of these stars and learning about, or delving into some of the stuff we've learned about. So we have two types of telescope. We have a reflecting telescope, which is this one, and a refracting telescope. So the refracting telescopes were the first ones, kind of like a pirate scope. You look straight through it and you have a couple of lenses in there. The reflecting telescope has a mirror. All right, so there's a lens for your eye, but you have a mirror, and the mirror tends to capture a sharper image for us, and so they actually are a better scope right there. So here's how the refractor works. Just goes through a couple lenses to our eye, and our lens in our eye right here. Okay, we get a focal point, and we see it, focused there. Here, the light comes in, has a big mirror which it can reflect off of, and we have our mirror and our lenses right there. So it actually has less opportunity for the lens to distort anything, so we end up with a sharper image. We also have radio telescopes where the radio waves are captured, and then they are collected into these. You've seen these probably, or at least in movies, right? And they feed it into here, and then it goes actually to a computer, and the computer gives us an idea of what we're looking at, and that is helpful for things that are far away, that are farther away, like a distant galaxy of some sort. Here are some regular, very large telescopes, very large reflecting telescopes. They typically have these. This might actually be McDonald Observatory in Texas. It reminds me of it. I might be wrong on that. They tend to like to put telescopes in desert areas. You can imagine that because there are fewer clouds to get in the way. Also high up, so that, technically, literally, the air's a little thinner there. And so mountainous regions, like for instance, there's a really famous one in Hawaii. You think, well, Hawaii is more tropical, but what they have, it's so high up that it actually is usually above the weather. Okay, so usually the clouds are below the mountaintop, creating all that tropical weather, and they end up with a pretty good image coming from that telescope. But getting out of the atmosphere, like Edwin Hubble suggested, we have done that with this. This is the Hubble Space Telescope. It's a reflecting telescope. There's a massive convex mirror right in here, concave mirror right in here, and it's collecting data and sending that data back to the Earth. And we have received from it some incredible images. I will tell you this: when they first devised this, they did all of the math calculations for the parabola of the mirror. They took the space shuttle up, put it up into space, got it going, and all the pictures came back blurry. And they thought, what went wrong? They went back and checked their math. They realized they were off on their calculations of the calculus of that curve just a little bit, and it did not focus properly. So trying to work on moving the focal point and that kind of thing remotely from the Earth, they did a little bit of that. But what they basically had to do was to replace that mirror. So they had to take these massive mirrors, very expensive, up on another space shuttle, put it up there, installed that mirror, and now we get these incredible images. Something like this. That looks like a nebula, right? This is a famous one. I will tell you, this is called, now I'm a little confused. I always thought this one was called the Horsehead Nebula, but then I saw a video that called it something else, so I don't know exactly. Do you see a horse head in there? Maybe this? I don't know, but it's famous and quite beautiful. Oh, and here we are, gang. We're at the end. It might be fun to go look up other Hubble Space Telescope images, because those are some of the older ones, some of the first ones they found, and so they probably have some really cool ones. All right, so I'm going to do our little film canister here. You can watch me do it and then go do it yourself if you haven't already. All right, let's see how I didn't do very well, actually. Okay, y'all, we're going to do our little rocket launch thing today. So you've got your little fizzing tablet. So I took it out and I broke mine. It kind of broke into these two parts right here. Okay, then you're going to take your film canister, all right, and I put some water in there, maybe about a third full, maybe a quarter full or something like that. And so what we're going to do is we're going to drop the tablets in, put the lid on quickly, snap it on, turn the whole thing upside down and set it down and walk away, all right? Don't stand too close to it. All right, let me get the lid ready. All right, here we go. All right, so I'm going to drop these in. I'm going to put the lid on. I'm going to put it here. Can you see it? No.
Hope you can see it. Oh, did we get it?
All right. All right, so I kind of missed it a little bit, but you saw what happened. Furthermore, did you see how quickly it happened? I will tell you that I did use warm water, not hot, but warm. And so you can, you'll have a few pieces of your tablet left afterwards. So you can try it several ways. You can try cold water, hot water. If you wanted to, be brave and try vinegar. And see if that was any change at all. You could just make your own little experiment here. I do want you to write this up. I know it's going to be very difficult, if ever will I see your lab books again, but I believe you have a little lab write-up sheet. You're going to write up your rocket deal. Now, of course, this is not studying the stars or astrophysics or, nuclear fusion, anything like that. But what it is talking about is the laws of motion and how getting up into space someday, we need to, and even putting the space telescope up there, it required us to have that knowledge of the laws of motion, right? So remember that law right there would be the third law, which is for every action there's an equal and opposite reaction. All right, so go try. I did notice I'm outside when I did it. It does make a little bit of a mess. I will admit to you, when we were together in class, we actually do it right there in that room, right there in that classroom, and then we make the mess on the table mostly, and then clean it up. It's got a little bit of abrasive stuff, and it helps to actually clean the table a little bit. So have fun with that, y'all. And I wanted to sort of end our year with a little bit of a bang anyway, so we could have a little fun with it, right? Okay, well, listen, it's been a great year. I sure wish we had had a chance to get back together again. I will send out, let's see, if you're going to be watching this on the day of classes, which is Tuesday, then I will send out your... I will send to you on Monday this video and the corrected, not your corrected quizzes, but the quiz keys. Okay, so all the quiz keys. I'm not going to require you to take a quiz on Module 16, but I will send you a Module 16 quiz key for you to study. So I would study through those, through your corrected quizzes you had before spring break, for the ones I'm going to send you since spring break. And then I will post, as far as I know, y'all, I will post that online final exam on Wednesday. All right, and you can take it then and you'll be done. All right, you'll be done with class. And then once I've got that, I'll calculate your grade and I will send your grade to you. Okay, everybody's doing really great. Okay. Anyway, sure missed you these last few weeks. And I hope you have a fantastic summer. And then next year, hopefully I'll see some of you again as we continue on our ODA experience. Right now, ODA has decided we will indeed have live classes starting in September. And if we have to make adjustments after that, we will. Hopefully we'll get over the hysteria of all this and we'll all be okay. All right. Anyway, love y'all and have a great summer. Bye.